Now, this is a confusing looking diagram. Let me explain it because it's not really nearly as bad as it looks here. Okay, look at the left-hand side. We have light, which is monochromatic. You guys remember what that means, right? Monochromatic light is one color, yeah, one color. It's shining on these two openings. And of course, that monochromatic light, as it goes through those openings, diffracts like this, spreads out. But of course, those diffraction patterns end up overlapping. And as they overlap, we get an interference pattern. That interference pattern has antinode or bright line or maximum, dark line, bright line, dark, and so on, right? But we can't see those because the light's not reflecting off of anything. So we put a screen down here, and when we put a screen down here, this is what we see. Bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, and so on. This would be our central antinode, or central bright spot, or central maximum. Next one would be our first minimum, first order maximum, second minimum, second order maximum, and so on. Second order maximum, second order antinode, second order bright spot, whatever you want to call it. We can describe what happens here. We can describe the position of these antinodes, the angles involved, distances involved, and so on by two equations. And those two equations are written on the board right now. Lambda is equal to d sine theta over n. Lambda is equal to xd over n times L. Now, there's a big if right here that we'll talk about later on, not right now. Assume right now that it's just always good. But we do have to recognize what each of these variables mean, and they are a little bit more confusing than a simple equation like v equals d over t. Let's identify the easiest one first. Lambda represents wavelength, and we typically want to be in meters here. In either equation, lambda is the wavelength of the EMR in meters. So again, if we're talking about monochromatic light, red light, let's say, 10 to the minus 7 meters, that's what we're talking about here for lambda. D, little d, in both equations represents the distance between the slits. And that's going to be measured in meters as well. This is a little d right here, the distance between the slits. That's going to be a small number. Okay, Rachel saw when I showed her the diffraction grating that we used in our little demonstration here, she saw that those two slits were really, really close together. So that little d value is going to be a small number, especially when you record it in meters, it's going to be a small number. L, which only appears in the one equation, represents the distance from the slits to the screen. Now, I made that a capital L over here. It's a lowercase l in the equation. Doesn't really matter what you make it. I just didn't want to make it a lowercase l over there because it looks like a 1, right? I made it a capital L so that you can tell that it's supposed to be L versus the number 1. So we're going to say that's the distance between the slits and the screen. And what do you think we're going to measure that in? Meters, of course. Now, what I'm about to show you is going to look a little bit confusing. So bear with me on this, okay? I'm going to say that X is going to represent the distance from one maximum or minimum to another maximum or minimum. From one to another. Which one to which one? From any of them to any of them. Let me show you what I mean by that. This value, this can be X. This could be X. This could be X. This could be X. From any maximum or minimum to any other maximum or minimum. So how is it that we're going to get the same answer if Joshua has X going from first to the second, but then John has x going from the central maximum to the second. How can they both get the same answer? Yep. Yeah, exactly. N has got to be consistent with it. So whatever you use for x, that's fine, as long as your value of n is consistent with it. N is the difference in the maximum number. So here, if x is that distance from 1 to 2, n for that one would be 1. 2 minus 1 is 1. Here we'd say n, since we're going from 0 to 2, would be 2. 2 minus 0 is 2. Here we'd say n, we're going from 1 on the one side to 2 on the other side, n would be equal to 3. 2 minus 1 is 3. This one's a little bit trickier. What do you think this one is? We're going from the first order minimum or dark spot or node to the second order antinode. Yeah? Good. N would be 1.5 there. Right? We consider that to be 0.5 to 2 gives me 2 minus 0.5 is 1.5. So if John used this one, that's fine as long as he makes n 2. If Joshua used this one, that would be fine as long as he makes n 1. Somebody had a question there? Yep. You're good? Okay. Now no, n wouldn't be 0, no. It's the minimum value of n would be 0.5, and there wouldn't be a maximum value. All right, one more variable here, theta. Theta, of course, represents an angle, right? But what angle are we talking about here? The angle from the central maximum, always from the central, to the first order maximum, or it could be to the second order maximum, or it could be to the third order minimum. It can be from the central maximum to whatever you want. X is a little bit more general, a little bit more open, because x can be measured from anything to anything as long as n is consistent with it. Theta can be measured to whatever you want, but it has to be measured from the central maximum. You got to have the same starting point with theta, always from the central. And again, you got to make n consistent with that. So in this case, we'd make n 1 because we're going from 0 to 1. In this case, we'd make n 2 because we're going from the central maximum to the second order maximum. If we went to the second order minimum, n would be 1.5. 1.5 minus 0 is 1.5. Now, one more little thing before we actually put this into practice with some calculations here, all right? We started off this page by establishing that we had monochromatic light, one color of light. Usually it's red, because most lasers are red light. Okay? At least commonly available lasers are red light. You can get different colors, but most of them are going to be red. If we have red light, then we get this pattern where all of these maxima, or bright spots, that are formed on the screen are red. If we happen to use green, then we would get all of these maxima that were green, right? But if we're using something, a laser that was blue, then we get all of these bright spots that were blue. But the blue bright spots would not appear in the same place as the red light spots. If we have red light shining upon this, we would get an interference pattern that looked like this. Let's just draw it as single lines here. We got a red line, 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 and so on. This would be our central bright spot, our first order, our second order, our third order, and so on. If we had blue, then we would get something that looked like this. Notice the blues are in slightly different positions than the reds. If you look at my picture of the dark side of the moon over here, by Pink Floyd, my 137th favorite band of all time, 136 spots behind U2, you see that red light refracts the least. Red light diffracts the most. Do you see that? Red light spreads out the most. It bends the least, but it spreads out the most. You can see that the red maxima are further away from the central than the blue ones are. Okay, so if I use red, this is what I get. If I use blue, this is what I get. What if I had red and blue at the same time? What would you see? You would see red and blue together right here, and then you would see a distinct red line and a distinct blue line. That's what you'd see. This would still be our first order maximum and our second order maximum and third. We wouldn't say 1, 2, 3, 4. Okay, both of those would correspond to our first order maximum. Both of those would correspond to our second order maximum. What would you see if you had all the colors of the rainbow? Well, you would see red, orange, yellow, green, blue, indigo, and violet right there. In other words, you'd see white right there. And then you would see right here for the first order maximum, not Roy G. Biv, but Vibgyor, the opposite of Roy G. Biv. The opposite because we don't see red light diffracting the least like it refracts, rather it diffracts the most. It's the opposite of the spectrum. Does that make sense? So what happens if you get a problem? What happens if you get a problem where you have to solve for something, wavelength, D, theta, N, whatever, and you've got polychromatic light, not monochromatic light? Here's what I want you to do. Pick a color. If you have multiple colors, pick a color. Like let's say we have data about blue. You've got all these colors, but you've got data specifically about blue. Pretend that there is no red. Just pretend it's not there. If you've got 6 different colors and you've got data about yellow, pretend the other 5 aren't there. Just pretend that only yellow is there and do the question the same as you would do the question if it was just red back here. Does that make sense? Don't get confused by polychromatic light. It looks confusing because you see all these different colors on your spectrum, right? But just forget about them all, except for the one color for which you have data. Okay, I want to do one example. Oh, sorry, show you this picture here first, and then we'll do an example. Don't worry about writing this down. This picture just represents if we have individually red, orange, yellow, green, and blue light. Okay, individually, we'd see that this would be our central maximum right here, 0. This would be 1. This would be 2, 1, 2, and so on. You can see that the blue central maximum, 1, 2, you can see the blue ones are closer to the central maximum than the red ones. That's because blue light diffracted the least, red light diffracted the most. Now, the reality is because we have all these different colors, it doesn't end up forming a pattern quite as neat as this. If they were all together, it ends up forming a pattern kind of like this because you end up getting, say, the blue light from maximum 3 overlapping with the red light from maximum 2. So you get different spectra, but it ends up looking kind of, especially as you go further out, kind of just a hodgepodge of colors, it seems. Okay, let's take a look at an example and then we'll wrap it up for the day here, okay? This is from your textbook as well. Page 689, question 3.8. It says monochromatic light, or one color, although it doesn't really matter, right? If we had polychromatic light, all we'd have to do is look at one color specifically of the multiple colors. Monochromatic light is incident on 2 slits separated by this distance. Okay, that's little d, 0.30 millimeters, which I actually don't want to be in millimeters, so I'm going to convert that to meters by multiplying it by 10 to the minus 3. I can move the decimal place over, but I don't like doing that, so I'm just going to tack on a 10 to the minus 3. My angle, theta, is 0.080 degrees, and that theta has to be measured from the central maximum to some other maximum. Here we're talking about the first antinode. What would n be there? 1 minus 0 is 1. Looking for the wavelength here. Let's use the first equation, the one that didn't have the big if beside it. D sine theta over n. D is 0.30 times 10 to the minus 3. Theta is 0.080. N is 1. Do this. We get 0.3 times 10 to the minus 3 times sine. Sorry, that's not 0.080. It's sine of 0.080. And we divide that by 1. We get 4.2 times 10 to the minus 7. That's the wavelength of the light that was used here. If it was polychromatic light, well, then that would be the wavelength of the one that corresponded to that angle. If we had a slightly different angle, it would correspond to a slightly different wavelength. So remember here, besides all the variables and the equations and so on, remember, with refraction, red light or small frequencies refract the least. High frequencies or blue light refracts the most. With diffraction, it's the other way around. Red light or low frequencies diffract the most. Blue light or high frequencies diffract the least. So with refraction, you get Roy G. Biv. With diffraction interference, you get Viv G. Orr. All right. You got a couple questions here that I'd like you to work on page 689 in class. All right. Let's take a look at that second equation now that had that big if. Remember, lambda is equal to x d over n times L if ... And I told you that I'd tell you what that big if meant in a little while. Now I'm going to tell you. We know the variables here, right? X is the distance between maxima or minima. D is the distance between the slits. N just has to be consistent with X. L is from the slits to the screen. Well, what's the big if? Well, the equation that we've just used, d sine theta over n, is perfectly valid anytime. It is a good equation. It is derived exactly from the geometry of the interference pattern that we would find. This equation is actually an approximation. It's not actually perfect. Okay, we make an approximation as we're deriving this equation. But it's a really, really good approximation at small angles. When the angle is small, this works really, really well. Even though it's not perfect, it works really, really well. If theta is less than about 10 degrees, we say this equation is good. If it's bigger than 10 degrees, then the approximation becomes not as good. So we don't want to use this equation above about 10 degrees. But we have to have, or at least in my mind, we have to have a different way of determining whether we can use it or not, other than determining the angle. Listen, if we're given a question where we have the angle given to us, let's say it's 6 degrees. Well, why wouldn't you just use this equation? Lambda is equal to d sine theta over n if you're given the angle. Right? If we're told that it's 6 degrees, yeah, it's under 10, and we could use it with this, but why would we? If we're given that it's 6 degrees, why wouldn't we just use this? So this becomes useful if we don't know what the angle is. Maybe it's bigger than 10 degrees, maybe it isn't. We have to determine what the angle is in order to use this, to make sure that it's under 10 degrees. But if we have to determine what the angle is, well, then why wouldn't we just use this? So what's the value of this second equation? Either we have the angle or we got to find the angle, right? Well, I have this little rule of thumb, and this is just my little thing. So if you ever go on and take this in university, you probably won't see this little thing, but it'll still work. Okay, even though somebody else might not teach it to you, it'll still work. My little thing is a rule of thumb. The rule of thumb is this. Is L greater than 10 times x? If it is, then the angle will be less than 10 degrees. So in other words, we can determine whether this equation is valid or not without bothering to determine what the angle is. We may not know what the angle is, but at least we know it's less than 10 degrees or not. We know that we can use that equation or not. Is L greater than 10 times x? So if you have a value of x and it's 0.5, 10x would be 5. If L is 6, you're good to go. If L is 4, then you're not good to go. This equation couldn't be used. You'd have to find the angle then and use the other one. I'll show you how to find the angle in a little while. Okay, let's take a look at an example here that's based on that equation. 13.9 on 691, it says a student measuring the wavelength of light emitted by krypton gas directs the light through two slits separated by 0.264 millimeters. Interference pattern is created. The screen 3 meters away. Here's the distance. What's one of the wavelengths of light emitted by krypton gas? What are they kind of telling me if we read between the lines there? What is one of the wavelengths? There's more than one. But one wavelength will produce this data. Another wavelength will produce different data. What did I say to do if you have more than one wavelength? Pick one. We're going to pick this data, and we're going to get the wavelength that's associated with this data. Right? It doesn't matter that there's more than one color. We have data for one. Let's go with it. So what do we got here? We got D is 0.264 times 10 to the minus 3 meters. 0.264 millimeters. L is 3 meters. We're going to say N. We're going from the second bright spot to the central. N would be equal to 2. And X would be 1.18 times 10 to the minus 2. Or you could say 0.0118. What happens if you go to XD over N times L? If theta is greater than 10 degrees. Is theta greater than 10 degrees? I don't know. I don't know what theta is. So let's do our little check. It's 1.18 times 10 to the minus 2 because it was 1.18 centimeters. And we want to convert that to meters. Okay, what's the value of 10x? X was 1.18 times 10 to the minus 2. 10x is 1.18 times 10 to the minus 1. L is 3. Is L greater than 10 times x? It's way bigger than 10x, right? Somebody this morning said, what if 10x is really, really close to L? Can we do it then? Yes. This little rule of thumb that I've come up with errs on the side of caution. So even if 10x is equal to L, you're still good. Just don't use it if it's greater than L, that's all. Okay, so we're good. We can use this equation. X is 1.18 times 10 to the minus 2 times D, which is 0.264 times 10 to the minus 3. N is 2, and L is 3. (1.18 times 10 to the minus 2 times 0.264 times 10 to the minus 3. We're going to divide that by 6. 5.2 times 10 to the minus 7. Good there? Quick question though. What would we have done there? What would we have done if 10x was 3.1? What if L wasn't greater than 10 times x? Right? Find the angle. Yeah, just find the angle. This would be x, the distance from maximum to maximum. This would be L, the distance from the slits to the screen. This would be theta. Just find the angle. We could do that every time, but if we do that every time, then why wouldn't we just use the other equation, d sine theta over n? Okay. By using this little trick right here, this little rule of thumb, we avoid having to do this most times. The only time we have to do this is if L is not greater than 10 times x. If it's not, find the angle and then use the other equation. All right, I'm going to give you a few minutes here to work on 3 questions on page 691. Be careful on these. Pay attention to little things like third dark fringe, central antinode. 0.5, whole numbers, 0.5s. Whole numbers, 0.5s. Okay, watch out for little things like that, okay? See what you can do here. Last example for the day on page 693 says, a diffraction grating has 1,000 lines per centimeter. What does that mean? Well, this is a diffraction grating where you have 2 openings, right? We also call that a double slit experiment. Specifically, it's sometimes called Young's double slit experiment, named after a guy named Thomas Young who did this experiment first. 2 slits, diffraction grating, whatever, right? The distance between those slits is, of course, called little d. Now, a diffraction grating is more typically a term that's associated with a situation where you have not 2 openings, but lots of openings like this. Maybe you have, as in this case, 1, 2, 3, 4, 5, 6, 7 openings, or maybe you even have 1,000 openings per centimeter. A diffraction grating has multiple openings, usually more than 2. Now, the distance between openings is still given by the symbol d, but we're not typically in one of these questions given the value of d. Rather, instead of being given the centimeters per line, or centimeters in between lines, we're given the lines per centimeter. So as opposed to this value being d, this value would actually be 1 over d. Right? Centimeters in between lines is d. Lines per centimeter is the inverse of d. So what do you do to get d? All you're going to do is say d is equal to 1 over 1,000. And when you calculate that, it ends up being 1.00 times 10 to the negative 3 centimeters, which we want to convert to meters. So we're going to make it 1.00 times 10 to the negative 5 meters. If you got lines per centimeter, lines per meter, flip it over, get d. Because you got 1 over d, get d. And then convert it to meters after that. So there's the value of d. When light passes through the grating, an interference pattern is produced on a screen 4 meters away. This is L. The first order bright fringe, central, first order, middle, n is going to be equal to 1. X is 19.2 centimeters, or 0.192 meters. What's the wavelength? We won't worry about the color. We want to use this equation, but can we? X is 0.192, multiplied by 10, 1.92. L is 4. Is L greater than 10 times X? Yeah. So it's okay to use that one. X was 0.192. D is 1 times 10 to the negative 5. N is 1. L is 4. So we're going to say 0.192 times 1 times 10 to the negative 5, divided by 4, 4.8 times 10 to the minus 7. Remember, if L wasn't greater than 10 times X, then find theta. Find theta using this. Here's X, here's L, here's theta. Tan theta is equal to X over L. And then use the other equation. That's it. These questions aren't any different than the 3 questions you were just working on, except that you got to convert 1 over d to d. All right, 3 questions to go along with that on page 693. But I'm going to caution you. Question number 1. Be really, really careful with your comparison here. L. Okay, be really, really careful with that. And I'll also caution you that the answer for number 1 that's given in your book, it's not listed down here, but the answer that's given in your book is incorrect. The answer for number 1 is incorrect. So what are you going to work on right now? Page 691, what you were just working on a few minutes ago, and page 693. Those are going to be due for Wednesday.